We still have one problem in equilibrium. The symmetrical shelf is subjected to uniform pressure P. Support is provided by a bolt or pin located at each end A and A prime, and by the symmetrical brace arms which wear against the smooth wall on both sides at B and B prime. Determine the force resisted by each bolt at the wall and the normal force at B for equilibrium. So here we have a distributed load in 3D. Okay. If you remember, we said that if we have a distributed load in 3D, then the resultant is equal to the volume formed by the distributed load. And of course, it should pass by the centroid of the volume. Okay. So here first, the first step is to reduce this distributed load into a force. So first we say that the resultant will be just at the middle of our beam, like this. Its value will be equal to the volume. So the resultant force will be equal to the pressure times the area on which it is applied. So times B times C. Now, because of symmetry, okay, the majority of time, symmetry will give you information to simplify the analysis of your problem. So when you have symmetry, complete symmetry, then it's like your load, an equivalent system will be to divide your load in two parts, one at the first end and one at the other end of your beam. So this system will be equivalent to two equal forces acting at the center at each end. Okay, so if I put here a force of PBC over 2 and here PBC over 2, I don't change anything because I have the same resultant in this way. And also, if I do sum of moments about this point, it will be 0. So they are equivalent because this force is passing by this point. So no moment about this point. If I divide it into two equal forces at each end, the moment will still be 0 because these two forces will do opposite moments. Okay. And I have the total force is the same. So these two systems are equivalent. And in this way, I can easily find the reactions because by symmetry, the reaction at this end here will be equal to the reaction at the other end. So it's enough to do the analysis on one of the two ends, considering that each end is subjected to a force of PBC over 2. Okay, so in this way, we have transformed our problem from 3D equilibrium to 2D equilibrium. So now, if we just consider one end of the two, and we draw the free body diagram, they said that at A we have a pin, and at B it's like it's a roller. So at A we have AX, AY, and at B we have only the normal reaction perpendicular to contact. And the force applied will be at the center of the end, okay, equal in magnitude to PB times C over 2. And the distance, we know that this distance is B, so it's applied just at the middle. So now, all we have to do to find AX, AY, and NB is to do the equilibrium equation because we have three unknowns, AX, AY, and NB. So the first relation can be sum of forces along X. Along X, we only have AX and NB. So we can write that plus NB minus AX equal to 0. So the first relation will give us that AX is equal to NB. Now, the second relation is sum of y equals 0. If we do sum of y equals 0, we have only AY and the known force here. So AY should be equal to PBC over 2. So this will give us AY. We still need the third relation to close the system. So we can do sum of moments about any point in the figure. In particular, A is the best choice because AX and AY both pass by A. So if we do sum of moments about A, choosing a positive direction, so let us consider that the counterclockwise is positive. Then we will have plus NB times the distance A And for P, it's a clockwise moment, so it's minus PBC over 2 times this distance, which is B over 2. In this equation, the only unknown will be the normal reaction at B. So from this relation, we can get the value of NB and then replace it into sum of X to get the value of AX. Okay. Now, they ask for the magnitude of the reaction at the pin. So all I have to do is, once I have AX, AY, I do radical of AX squared plus AY squared. Okay. Any question on this? Okay, so we are done with chapter of equilibrium of a rigid body. We will now start the final chapter in statics part, which is internal forces. And you will see that in the majority of this part of internal forces is already covered before, and it's just a small new application. So what do we mean by internal forces? When we talk about internal forces, this means that we are taking into consideration what is happening inside the structure. So in general, if I give you a beam, I give you external load on it, and I give you that it's supported, for example, by a pin and a roller, okay? You can calculate, let's say, external reactions. The external reactions will be reactions that come from supports, okay? So these are called external load. These are called support reaction here at B, at A and B. Now, what is happening inside the structure? So if I am interested to know what is happening inside my structure, I should do a cut. Because if I look at it from outside, the internal forces will not appear because they will cancel each other. Okay, so in order to be able to calculate internal forces, I should cut my structure. When I cut my structure and divide it into two parts, the two parts will have action reaction on each other. So what is happening inside the structure is called internal forces. And each material, you know that each material has a certain limit that, so for example, it cannot support, for example, in tension, let's say, more than 1000 kilonewton, for example. So I should make sure that the internal forces, if I calculate tension, internal tension, it should not exceed the limit of my material. So this is why it's very interesting to know how the internal forces are varying over my beam for proper design. Okay, so this is the objective of this chapter. Now, what are internal forces? So internal forces in a structure can be determined by cutting it into two parts using the section method. So for example here, if you are interested to know what is happening at point B, you just do a section at B. This will divide your beam into two parts. The first part is this one, and the second part is the other one. But by action reaction, okay, the forces acting on B should be equal in magnitude, opposite in direction for the two parts. From here, we have a convention, okay? So if I do a cut at B, if I do a certain cut at B, okay, I will consider that the type of possible internal forces and moment that I can have. First is a tension force, okay? So I will consider that the N is positive if it's causing tension, and N is negative if it's causing compression of the beam, of this part of the beam, okay? So to calculate N, all I have to do is to apply sum of X equals 0. So here, for example, before doing the cut, what should I do? Before doing the cut, since I have here a fixity, the first step is to calculate the reaction at the fixity. You know already that if I have external load, I can calculate what will be the resultant fixity reactions. So I will have at fixity AX, AY, and couple moment MA. But these are calculated already before. And before doing the cut, I do sum of forces and sum of moments equal to 0. I get AX, I calculate AX, AY, MA. So these are given, are calculated already. Once I know them, when I do the cut, to find the internal reactions, which are the normal force, which is causing tension to the beam. The force, this one is called shear force, okay? V, the symbol of it is V. And we have what is called the bending moment, which will tend to bend the structure. So it is the bending moment M at B. To calculate these three internal forces and couple, we should write the equilibrium equation. So if you want, it's just like when I do the cut, the internal forces become external. Okay. So now to get the NB, all I have to do is to say that sum of forces along X on this part is equal to 0. So I have plus AX plus NB equal to 0. Here you will get negative NB. So your beam is in, at B, your beam is in compression. Okay. And to get VB, you do sum of Y on this part equals to 0. So you will get plus AY minus VB equals to 0. So AY equals to VB. And finally, to get the bending moment, MB, you will do sum of moments about any point of your structure. So you can do it about A, you can do it about B. In general, okay, to get MB, why we do it about B? To not have to include the moment of shear. And if you take sum of moment about A, should include the moment of shear force about A. And if you have calculation error for the shear force, this will give you a wrong bending moment. So it's better to take sum of moments about B. Okay. Now, if you take the left part of the beam, or you take the right part of the beam, you will get the same result for VB and BMB, because as you can see, we have selected them in a way to be opposite by action reaction. So we have a convention. What is the convention? As a normal force is always causing tension. So on this part, it will be to the right, while on the other part of the beam, it will be to the left. So if we calculate NB here or here, we will get the same result. Okay. Now for the shear, what is the convention for the shear? The shear is positive if it's rotating clockwise about the end of the beam. So here, if I take the left part of the beam, this is the end. VB should rotate clockwise about it, so it should be downward. While if I take the other part of the beam, this is the other end, VB should rotate clockwise. So to rotate clockwise, it should be upward. So as you can see here from the convention, this will ensure opposite shear forces at the different parts of the beam. And we know that by action reaction, they should be opposite. This is why if I calculate them from the left part or from the right part, I will obtain the same values for NB, VB, and MB. Okay. Now, what is the convention for the bending moment? The bending moment is positive when it compresses the upper part of the beam. Okay, so here, if I take this part, the bending moment should be counterclockwise to compress this part, the upper part. While if I take the right part of the beam, I should take the bending moment clockwise to compress the upper part. Okay, so this is the convention used to determine internal forces in 2D. Now, as we seen together in 2D, we have for the internal forces and couple, we have the shear force, which is along the section plane. We have the normal force, which is perpendicular to the section plane, and we have the bending moment. Okay, the bending moment, which tend to compress the upper part. Okay. So this is in 2D. In 3D, it is more complex. In 3D, we have 3 forces and 3 couples at the section. Okay, so whenever you do a section, you say that this section is in equilibrium. So I should have internal forces here to maintain equilibrium. The internal forces will be divided into 3 components. We have V along X, V along the Y. Or here, if you want, they call it the component perpendicular to the section, they call it N, so it's a normal force. While in 3D, the shear will be divided in two components in the plane, because here you have a 3D case, so you might have forces in X and you might have forces in Z. So you have two components for shear in 3D, in X and in Z. While in 2D, the shear component will only be along one direction. Okay, so these are concerning internal forces. For internal moments, okay, in 3D you have a torsional moment, so you can have torsion of your structure. Okay, the torsion moment will be perpendicular to the section, while you will have two bending moment components, one along Z, one along X. So the couple moment along the axis of the cross section of the section plane are bending moments, while the moment perpendicular to the cross section plane is a torsional moment. It will cause torsion of my structure. Okay, and to calculate internal forces in 3D, it's the same concept. I do a cut and I have, let's say, some external load here. I say that to have equilibrium, the condition is that sum of forces and sum of moment on this part is equal to 0. And in this way, I can determine the internal forces and moments at any section I want. Any question on this? Let us do some problem to practice on internal forces. So we have here a beam subjected to a distributed load. We want to determine the normal force, shear force, and bending moment acting at point B of the two-member frame shown in the figure. So here, if you want, this chapter will be a summary of all chapters, because you will see in it how to some of the calculation of forces, the calculation of moments. So it's a review of equilibrium and the review of the distributed loads and moments, and plus that we will introduce the new concept of internal forces. So here we are interested in the internal forces at point B. Okay, before any calculation of internal forces, the first step is to determine the support reaction, because you will need them when you do the cut. Okay, so here you are interested in AC. First, AC is subjected to what? You have a pin at A, so you have at A, AX and AY, plus it is connected at C to a two force member CD. Whenever you have a two force member, we said that the force will be along the two force member. So here, the action of the two force member on the beam will be along DC. So it will be like this. Okay. So now, once we take AC, the part AC, we have only three unknowns, which are AX. So here, if I have AX, AY, two unknowns, and FDC, the third unknown. So to calculate the external reactions, all I have to do is to apply for my beam the equilibrium equation. If you want, no need to calculate all of them. Why? Because at the end, the question is not to find the external reactions. The question is to calculate the internal forces at B. So what you can say, you say, if I do a cut, what do I need to find the forces at B? If I do a cut at B, okay, I should know the value or of AX, AY or of FDC, because when I do a cut, I will just take one part. If you select to work on the left part of the beam, then you only need AX, AY. And if you decide to work on on the right part of the beam, then you only need FDC. Okay, so try to select the part which will minimize your calculation. So here, for example, I can say, since in the right part I only need to get FDC, So no need to get AX, AY also. Okay. So here I got all of the three, but you can reduce your calculation by knowing previously what is the part you want to select. So let's say you said, I want to work with this part, not with the other one. Okay. Because if you do the calculation on the left or right part, you will get same results at the end, because by action reaction, you have same internal forces, but in opposite directions. Okay, so here in opposite sense. So here, if I select to work on the right part, then at B, I will have, because it's 2D problem, I will have the normal force, which is positive if it's tend to cause tension. I have the shear force, which is positive if it tends to rotate clockwise about the end of my beam. And I have the couple moment, which will be considered as positive if it's compressing the upper part of the beam. So these are my three unknowns. To get them, I need to determine before what is FDC. Okay. Now to get FDC, I just need one equation, because if I take the whole beam, okay, and I do sum of moments about AX, AY will not do moments, so I will have only the moment of FDC. Okay. Now you have a distributed load acting on your beam, but you know that you can reduce this distributed load to one equivalent force. This equivalent force will act at the center of the beam at B, so it will be equal to 50 times 8, so it's equal to 400. Okay, my equivalent force is 400 lb, and it should pass by the centroid, which is B. So it will pass by point, okay, because the centroid is just above B, so it will pass here. Okay. Now, since I know I reduced my distributed load to one force, I can now calculate the value of FCD by doing sum of moments about A. When I do sum of moments about A, I will select a positive direction. They selected here the counterclockwise as positive. So as you can see here, the moment of the distributed load is clockwise, so I will take it as negative. So it's minus 400 times the distance from the equivalent load to point A, which is 4. So it's minus 40 times 4 plus the moment of FCD. Now concerning the moment of FCD about A, as you can see here, FCD can be divided into two components. One along X, which is passing by A, so it will not have any moment, and one along Y. Now, the Y component, if you look well at your figure, they gave you here a triangle to know the direction of your force. So it's 3, 4, 5. Okay, this is 3, this is 4, and this is 5. Okay, so now you can say that the component of FDC along Y can be calculated as, so FDCY is equal to FDC times sine of this angle here, which is 3 over 5. Okay, so times 3 over 5. And then to get the moment of this force, I should multiply FDY by this distance, which is 8. Okay, so you get minus 400 times 4 plus 3 over 5 FDC times 8. You get the value of FDC. You can calculate AX, AY, but it's not needed, because if you take this part, no need for AX, AY. On the other hand, if you want to get to work with the left part, you should calculate the values of AX and AY. Okay. Now, once we have FDC, we work on this part. We say to get the three internal forces and couple, then we should apply the equilibrium relations for this. Okay. Now, please pay attention for something. Never reduce your distributed load before the cut. Yeah. I did a reduction of the distributed load here in order to calculate the external reactions, okay? But when I want to determine internal forces, I cannot say that the internal forces will be equivalent if I have a concentrated force and if I have a distributed load. No. And here, if you consider that I have only a force at B, then when you do a cut, for example, here, you will not have any load acting on the B, which is not the case. Okay? So before, if you want to calculate internal forces, you do the cut, then you reduce the distributed load. So here, when I do the cut at B, what is acting on my remaining part is a distributed load. And this distributed load, I can now reduce it into one equivalent force. Okay? So I never reduce to equivalent force before doing the cut. Because if I reduced here to one force and if I do the cut now, okay, then I don't have anything on the start, which is not, if you want, I can reduce to an equivalent force to calculate external reactions, okay? But when I want to determine internal forces, I should put my distributed load as it is, and after doing the cut, I can reduce it, okay? So here, before doing the cut, I don't do the reduction. I say that my part BC is subjected to a distributed load. Now, calculate NV and M. I say that this force can be equivalent to one force passing by at the middle of my beam. Okay, to be able to calculate NV and M. So now, since I have the distributed load is 50 lb per feet, and here I have from B to C a distance of 4. So the equivalent force of this distributed load will act at the middle of my beam, of my part BC, okay? And it will be in magnitude equal to 50 times 4 equals to 200. So now I am ready to write the three equilibrium relations in order to get the values of N, V, and M. Okay? So to start with, I can write that sum of forces about X equal to 0. So the first relation will be sum of X equals to 0. So I have plus FCDX. So FCDX is FCD times 4 over 5. Minus NB equals to 0. So this will give me the value of NB, the internal force of tension. So NB is equal to FCD times 4 over 5. Now, for in Y, what do I have along Y? Sum of Y equals to 0. Along Y, I have the shear force, so plus VB minus 200 plus FDC times 3 over 5 equals to 0. So I can get the value of VB. And finally, to calculate the moment at B, I do sum of moments about B equals to 0. And I select a positive, for my equation, I select a positive direction. So I will take here the clockwise as positive. Okay. If I select the clockwise as positive, what do I have? I have plus MB. For the 200 force, it's doing a clockwise moment, so it's plus 200 times 2. And for FCD, okay, it's causing a counterclockwise moment, so it's minus, only Y component is doing a moment, so minus FDC Y, which is FDC times 3 over 5, times the distance, which is 4, equals to 0. So the only unknown in this equation will be MB. I can get the value of MB. And in this way, I got the internal, two internal forces and one internal moment at B. Okay? Any question on this? So you can see here what they did. they selected, as we did, they selected the left port, okay? And no, let me check. They selected AB. So you can check that you will obtain the same result. And they did the analysis on port AB. If you do the analysis on port BC, you can check that you should obtain the same numerical values. Okay. Another example, we said that we can determine internal forces in 2D and in 3D. So here we have a 3D problem, and the question is to determine the X, Y, Z components of internal loading at a section passing through point C in the pipe. Neglect the weight of the pipe and take F1 to be minus 80I plus 200J minus 300K, and F2 equals to 250I minus 150J minus 200K. What I want to tell you here that the selection of the part you want to work with will simplify a lot your calculation. Yani here, for example, this is a 3D structure and it is connected to a fixity at this point. But for the fixity here, I don't know the external, I don't know the reaction. I should calculate that. And if I want to calculate the reaction here, I should write sum of forces equals 0 and sum of moment equals 0 to get them. So I can try to select the part that is not containing the support. So this will simplify a lot my calculations. So here if I do a cut at C, instead of taking this part and work with, then I will have to calculate the reaction at the fixity. I say no, it's easier to take the other part. Because if I take this part, I know F1 and F2, so no need to calculate any external reaction here before doing the cut. So I will do the cut at C, and I will select the part on which I know the forces. So in this way, my calculation will be much more simplified. So now my work will be just on this part. And in order to calculate the internal moment and internal force at C, I will apply equilibrium relations on this part. That's it. Okay? So here, since we are working in 3D, the internal force at C will have 3 components. So I will have Fx, I will have Fy, I will have Fz to be calculated. And also I will have a couple moments that can be decomposed into X, Y, and Z. To find these 6 unknowns, I need 6 equations. So first, the first thing I will write is that sum of forces is equal to 0. Okay, this relation will give me that the force F1 plus the force F2 plus the internal force at C is equal to 0. So I deduce that the Fc is equal to minus F1 minus F2. And Fc will have 3 components, one along I, one along J, one along K. Okay. Now, to get the moment MC, I will do sum of moments about any point, and I will select here point C. If I do sum of moments about C equals to 0, I should take into consideration the couple. So I have couple MC, plus I should consider the moment of F1 about C, plus the moment of F2 about C equals to 0. Okay, so this will give me an additional equation, okay, in which the only unknown is vector MC. So it will give me MCX, MCY, and MCZ. We will continue this problem in the next session, so I will open a new session, okay?